Hello, class. So on this video, we're finally going to start covering new sections and a new topic. But before I do this, let me just comment that if you remember in the last video, we finished section 3.2/4.1. In terms of the exam that we're going to have on Friday, July 24th, that's the last section that comes in. Right? So I uploaded into Wire Courses, right? If you go to Files, Exams, then I don't know exactly where else where to go afterwards, but if you go to Files and then Exams, you should be able to find this file that I titled Exam 1 Information or something like that, Exam 1 Info. I sent a message about this, so you can check your inbox or your email. But anyways, in that file, what I have is a summary of all the sections that we covered that are going to come into the exam. Right? So basically all the sections we covered in chapter 1, in chapter 2, and then with some caveat with 2.8 that we covered basically 2.8 at the same time as we did 2.4. We did two theorems for existence and uniqueness. The second one that involves partial derivatives, I'm not going to ask you something about that in the exam. And then in terms of chapter 3, we're going to, and what's coming into the first exam is going to be chapter 3, section 3.2, and chapter 4, section 4.1. Right? So this is all summarized in that file, so make sure to read over it. So everything that we're covering now is not coming in the first exam. It's going to be material for the second exam. Okay? So I wanted to make a quick comment about that. And if you haven't emailed me yet about the time slot that I chose for the exam, I think I chose Friday 5 to 7:45 p.m. If you haven't messaged me if that's going to be a problem, then you have to do it as soon as possible. Okay, so that's that. We'll talk more about the exam on the videos for Thursday because on that day I'll be doing a review for the exam. So now we're going to enter this new topic, which I'm going to label or call second order homogeneous ODEs. If you remember in the past video, I mentioned that the point of introducing linear independence was to define a fundamental set of solutions on an interval. Right? Why? Because if we know the fundamental set of solutions of a differential equation on some interval, homogeneous differential equation, sorry, we can find the general solution just as a linear combination of the functions in that fundamental set. Right? So as I mentioned, we know how to find solutions to first order homogeneous ODEs. We can just use the integrating factor method. So how do we find solutions to higher order homogeneous ODEs, so order 2 and higher? Well, since we know that if we find a fundamental set of solutions on an interval, we know what the general solution is, then the question shifts to, if we have a second order homogeneous ODE, how do we find two linearly independent solutions on some interval? Right? And that's basically what we're going to do here. We're going to see how to find two linearly independent solutions to second order homogeneous ODEs with one caveat that we're going to restrict to the coefficients being constants. So if you remember the coefficients of the coefficients of the derivatives, right, can be expressions involving the independent variable and constants, right? So what I'm doing here is restricting so that I don't want to see any independent variables either. All I want to see is constants in front of the derivatives. So I'm going to write this as constant coefficients. Now, in terms of what sections we're covering in the book, we're basically going to be covering 3 sections at once. Right? We're going to be covering chapter 3 sections 3.1, 3.2, which we already covered basically, but I'm just going to include it here because it's in the middle, 3.3 up to 3.4. Right? So we're covering 3 sections. Again, 3.2 were already covered. So 3.1, 3.3, and 3.4 in the book. And again, I recommend that you follow the book, that you read over it. It's good supplemental material. And I also already uploaded practice problems for all of these sections, right? So I also mentioned in one of my messages that I uploaded practice problems basically for all of the sections we're going to cover. And I also uploaded scans of the book so that you can, of those problems specifically, so that you can try them even if you don't have the book, right? So I recommend that you go over that for the exam, obviously, but as we're covering each section, if you want to practice, I would recommend going over those practice problems because they are similar to the problems we do in class, so it gives you more practice. So let's go back to trying to find a fundamental set of solutions to a second order homogeneous ODE with constant coefficients. So first, let's write how a differential equation like this looks like. Right? So it's second order, homogeneous, and has constant coefficients. So in general, this differential equation looks like this. And since it's the first time, I'm going to write the variable x because it's not going to be clear. But from now on, it's always going to be the variable x for at least the purpose of this lecture. So if I stop writing derivatives, just assume that the independent variable is x. If I stop writing the independent variable, assume that it is x. Okay? So a second order homogeneous ODE with constant coefficients in general looks like this. You can see that it's homogeneous, right? Because everything that's not being multiplied by a derivative is 0. It's linear, right? Because what's in front of the derivatives, remember that the function itself is counted as a 0th derivative. So whatever's in front of the derivative are either constants or expressions involving x. In this particular case, they're constants. Right? And again, since they're constants, the coefficients are constants, we would say that this differential equation has constant coefficients. Okay, so where a, b, and c are constants, specifically they're real numbers. So we're only going to be working for real numbers in terms of the constants. Okay, so this is the setup. We want to find a way to find a general solution to this differential equation on some interval. And all we know, which we know from the previous section, is our goal is to find two linearly independent, the second order, right? So in order to find a fundamental set of solutions, we need two linearly independent solutions on some interval. So how do we do that? Well, look at this differential equation. Let's say we want to find a solution, right? So I'm just going to write y. And we want to find a solution, right? So what form can y have if we want it to be a solution? Well, notice what is going on. We're looking for a function such that if we have the function times a constant plus its derivative times a constant plus its second derivative times a constant, this equals 0. Another way you can think of this is we want these three terms here to cancel. Okay? What is one way in which we have a chance of these terms canceling? Well, if we chose a function whose derivative equals itself, so actually or a constant multiple of itself, let me write it like this. If we choose a function y whose first and second derivative are scalar multiples or multiples of y. Actually, so I use the word scalar. Scalar and constant means the same thing, but I've been using the word constants. So I'm just going to leave it as constant. So if we choose a function y, whose first and second derivatives are constant multiples of itself, we have a chance that these three terms, term 1, 2, and 3, cancel. When we add them, right? So why is this the case? Well, it's kind of obvious if we go through the work, right? So suppose we choose a function y whose derivative is a constant, and first and second derivative is a constant multiple of itself. So we don't know what the function is, but we can write that. What that means in, mathematically means that we want a function such that y prime is, let's say, so I'm using c there. So let's just use c1 times y. So I want its first derivative to be a constant multiple of itself. And we also want the second derivative to be a constant multiple of itself. So what happens if we plug this into the differential equation? Okay, so this differential equation, what do we get? So we get a times c2 y, right? Remember, this is y double prime, plus b times c1 y. This is y prime plus c y equals 0. And here you can see that it is possible for the terms to cancel, because what would we need? We can factor out the y out of each term. So we would be left with a times c2 plus b times c1 plus c y equals 0. So if we were to choose correct scalar multiples, in particular, if this equals 0, right, which is possible, right? These are all constants, right? So it's possible for a times c2 plus b times c1 plus c to be equal to 0. If that equals 0, then we would find that whatever y we chose is a solution, right? Because anything times 0 is 0. So that's why this approach works. That's why if we look for solutions that satisfy this property, basically that the first and second derivative are constant multiples of itself, then we have a chance for this solution to satisfy the differential equation, as long as these coefficients add up to 0, right? As long as those coefficients cancel, right? So that's the idea. So that's why we're going to look for a function with that property, right? A function y whose derivative, first and second derivatives, are just constant multiple of itself, like we wrote here. So now let's look for an explicit function, right? Because here we wrote it generally. Do we know of any function whose derivative, whether it's the first, second, and in fact, for this case, any derivative is going to be a constant multiple of itself? Well, we know one, right? It's a function we like to work with a lot because of this particular property, and that function is the exponential. So notice that y equal to e to the rx, right? So I don't want to use just e to the x, because if I use just e to the x, then these coefficients here are going to be 1. That kind of restricts the solutions, because then we would want a plus b plus c to be equal to 0. So basically, we would only have solutions when the differential equation has the right form, right? When a plus b plus c equals 0. I want to make it more general. Right? I want to make it more general, meaning that I want to have more control, more degrees of freedom. So instead of just choosing y to be e to the x, I'm going to add a constant r in front, so that when I take the derivative, I get constants in front of the derivative, or in front of y. Okay? So notice that y equals e to the rx, where r is a constant, and a real number, satisfies the property that we're looking for. Satisfies the property that its first and second derivatives, and in fact, this works for any order derivatives. So let me write, in fact, any order derivative. But in this case, we're focusing on first and second because we're working with second order differential equations. But this works in general for any order derivative, right? So y equals e to the rx, or r is a constant, satisfies the property that its first and second, and in general, any order derivative, is a scalar multiple. Wait, sorry, I keep saying scalar. It's from linear algebra. So that's why I keep saying scalar. Satisfies the property that its first and second, and in general, any order derivative, is a constant multiple of itself. So in the previous part, we explained why are we looking for a function whose first and second derivatives are a constant multiple of itself, because if we do that, we have a chance of finding a solution, right? It's going to depend on this equation here, or this factor, being 0. And now here, I'm telling you that this is one such function that we know that satisfies this property. So let's do the same thing we did before, but now let's use this specific function, y equals e to the Rx. Right? So again, the differential equation is a times y double prime plus b y prime plus cy equals 0, where a, b, and c are constants. Okay, let's find, we're going to plug in y equals e to the Rx, and we're leaving r as arbitrary again because we want to have degrees of freedom in terms of how to solve this, or in terms of what makes that expression equal to 0, right? That constant expression equal to 0. So we need to find its first and second derivative. Let's do that here. So y prime, just bring the constant in front. Y double prime, you bring the constant in front again. So let's go ahead and plug this into the differential equation and see what we get. So let's use, say, green. So a times r squared e to the Rx, this is y double prime, plus b times r e to the Rx, right? This is y prime, plus cy, y is e to the Rx, equals 0. Right? So all I did was plug in y equals e to the Rx into this differential equation. So actually, let me make a note here that we're using y equals e to the Rx. Now, let's do the same thing as we did before. Let's factor out e to the Rx. So we have a times r squared plus b times r plus c times e to the Rx equals 0. Now, there's something about this expression here that I didn't mention. And the thing is, the only way a product is equal to 0 is if each of the factors, either one, the other, or both, is equal to 0. So in this case, in this equation here, if y equals 0, it's possible for this expression that's underlined not to be equal to 0. And I don't want that. Why? Because I don't want to use the solution y equals 0. And why is that the case? Well, y equals 0 is never linearly independent. Right? You could verify it using the definition or using the Wronskian with any other function, but I'm just telling you, y equals 0 is never part of a fundamental set of solutions. Right? So I don't want to include the solution y equals 0. So what I want for, or what would be ideal, would be for y to not be equal to 0 on some interval, and that would force this constant expression here to be equal to 0. That way, I wouldn't need to use y equals 0 as one of the solutions, because again, it's not part of a fundamental set of solutions, because it's never linearly independent. And that actually is satisfied if I use this function. Why? Notice that e to the Rx is never equal to 0, right? Look at the graph. The graph looks something like this. In general, it looks something like this. Oh, okay, let me use a different color. Right, the graph looks something like this. For e to the x, right, what is the r doing? It's either reflecting about the y-axis or stretching and compressing horizontally. In either case, no matter what r is, I just want to erase this arrow. In either case, no matter what r is, it's never going to make e to the Rx cross the x-axis, meaning that e to the Rx is never equal to 0. And again, by what I explained just a couple minutes ago, that's good, because I want this to be 0 so that, and y to not be equal to 0, because I don't want to use the solution y equals 0. So note that e to the Rx is never equal to 0. So it doesn't matter what r or x are. So what does it mean for us? It means that, so let me call this equation star. The only way star is true, so that equation is true, is if, well, the other factor is 0. What's the other factor? Well, it's a times r squared plus br plus c equals 0. So what does this mean? What this means is if we can find solutions to this polynomial equation, right? It's just a second degree polynomial with constant coefficients equal to 0. So in other words, if we can find the roots of this polynomial equation, and notice it has two roots, right? Because it's second degree. The only problem is that those roots might not necessarily be real, but we'll talk about that later. But in summary, if we can find two roots for this differential equation, we can plug them in, right? So roots in terms of r. Think of this differential equation, or think of this polynomial equation as r being the variable that we're trying to solve for. We can find two variables r for which this is true. Then we could potentially find two solutions. And if they're linearly independent, right, we know that there are solutions by construction, right? Because we know that whatever value of r we choose is going to make this equation equal to 0. And if they're linearly independent, then we're going to have a fundamental set of solutions in some interval. What that means is, in order for us to find two linearly independent solutions to this differential equation, it's going to be equivalent for us to finding solutions to this polynomial. So we went from a calculus problem, right, working with derivatives, to an algebra problem, working with just polynomials. And that's the general idea. That's the reasoning for why this process works. And I show you the mindset because I want you to see how you can approach problems like this. Why? Because some of you might go on and work in areas where you might have to come up with solutions to differential equations that you don't know solutions for. So you can always try to approximate, but let's say that you can find actual solutions in the terms that they're analytic, right? They're exact solutions, not approximations. That would be nice. And going through the mindset of how you can approach a problem like this, I think it's good because it gets you in that sort of mindset and that sort of thinking. There are things you can do just with a little bit of information to try to find a way to find, in this case, solutions that are exact solutions. So I think it's very important for us to go through the whole mindset. But that's the idea. So in summary, we started with a differential equation, second order homogeneous with constant coefficients. We're trying to find a fundamental set, and we saw that in order to find that fundamental set, it's equivalent to finding solutions to this polynomial equation in R.